Okay, so hi everyone. Um, yeah, in this talk, I would just like to just continue on what we have discussed before in the class about state space representation of the plant or of the system, and about the linearization a little bit about the linearization on the nonlinear system, right? So yeah, so we begin with the concept of modern control that we have also already touched before. So by using a state space concept or state concept, we are able to um, to handle the system with multiple inputs and multiple outputs, and we are also able to handle the more complex structure of the controller and of the system. And this is, I think, the idea that has been around for quite some time, and um, yeah, there are several, or there are many designs or many approaches based on this modern control and the state space representation. And yeah, several comparisons between modern one and the conventional one. Well, conventional here refers to the use of transfer functions, which could only be used for linear time invariant system, right, with single input and single output. Whereas for modern control, well, state space itself is also used only for linear system, but it allows multiple input and multiple outputs, as well as it could handle, or it could um, consider like several characteristics of the system by changing several matrices, and from that we could see, yeah, how the system could be controlled, right? And it's yeah, in conventional control we use frequency domain approach with uh, Laplace transform, of course, and with yeah, with frequency complex domain, whereas in the state space approach, we use just a matrix, which is actually representing the evolution of the system over time. Well, these are several plants or several systems that could be controlled with the state space approach. Even for like nonlinear system, in that case, we need to make them linear, of course. And yeah, it's useful to have a state space here because these systems often have multiple inputs and multiple outputs, and we need to know which inputs that we focus on and which output that we focus on measuring. So state itself is just a small set of variables such that knowledge of these variables at t equals t0 together with the knowledge of the input for t more than or equal t0, it completely determines the behavior of the system for that time, right? So in some ways, it's similar to transfer functions. It's not really, um, it could be the same with, or it could be the same for different physical systems. It does not, uh, yeah, it does not take account, or it does not, or yeah, how to say this is, it alone could represent or could determine how the system behaves, right, over time. And it's not limited to certain systems only, but it's applicable to many classes of systems. And it is just a bunch of variables, which is denoted by x1 and x2 and so on until xn, which is the order of the system. And this is the equation of the state equation. So we have the state here, x1, x2 until xn, and we have the input u1, u2 until ur, and the output is y1 until yn, and we have several functions here, two functions. So this function is an input to state, whereas this is state to output. Right? So the important um, variables, the most important ones are actually this one, right? This will determine how the system behaves, whereas for the output, it determines uh, the observability of the system. Uh, that means that given the output, how can we know the state, for example, right? So these are several problems that are useful to study, right? Because, well, in a system, there could be many states, right? If we are talking about like a DC motor, for example, the simplest example, uh, we could measure the speed of that motor, right? But uh, the state is not only the speed, right? So the state also includes, for example, acceleration and the position. So if we know the speed, could we know the acceleration, for example, or if we know the position, could we know the speed? So the output is only the speed, but the state itself could be three of them or even more for more complex systems, right? So that's the difference between the output and the state. The state is like the internal value in the system that we don't always know, right? Whereas output, it is the one that we could observe. So the equations, they are described as this: x dot is ax plus bu, and y is cx plus du. So this is the linear for linear system. So A is a matrix. So this is a matrix. B is a vector. C is a vector, and D is also a vector. Right? But yeah, again, the most important here is this one. X is the state. So I think most often or often people focus on this equation only for some systems because this equation dictates how the state evolves, and it dictates if we put uh, like a control algorithm, it would change U, right? So how changing U impacts the state's value or X. The bottom one is also useful, but it's not as often used as in the top one. So again, this represents how we can measure the output or which output that could be measured. Here, this is the block diagram of this state space equation. So we have, of course, the vector B here, and we have the matrices by matrix A and other vectors such as C and D. So Y again is the output, and U is the control signal or the input. So suppose that this is the plant, right, or the system, right? So this is the plant of the process, let's say. Uh, there is like an internal feedback that happens here, uh, which is dictated by the matrix A again, right? So matrix A and or this loop it converts the UB into X, right? So the main dynamic of this process or of this plant actually happens in this small feedback loop. So it is important to know which value of A, for example, that makes the system stable, or which value of A that is desirable for the system, for example. Well, of course, we cannot change the value of A, but what we can change is this U value. So this could be um, from the controller, let's say a PID controller or even a feedback controller that is used in the feedback loop. So this is the replacement or maybe other version of this transfer function of the plant that we have seen several times, for example. Right, so we replace this 2 over s plus 1 with this matrix. Right. Yeah, as I just mentioned, this is some or other representation other than transfer function representation of the system's dynamics. And for the transfer function, we have the input u processed by the transfer function g into the output y, whereas for the state space, we have this equation, right? Again, with matrix A and vectors B, C, D. And with this, uh, we could actually change this matrix or these vectors into the transfer function g. Right? So how we do this is, yeah, we calculate or we compute this equation, which is based on matrices, right? So S is just the variable S. I is the identity matrix, and Si minus A inverse, which is pre-multiplied by C, and then this will be multiplied by D, sorry, by B, and then it would be added D. And yeah, since this includes matrix, for some, well, for some complex system, it might be hard, right? Because we have to do the inverse, and for higher dimension, it's significantly harder to perform the inverse operation. Right? So just keep in mind of this. Yeah, so this is yeah, just the previous slide. So maybe I just want to uh, put some remark here that again, the most important aspect is here. Actually, like D is often assumed to be zero because it's rare that the output is directly affected by the input of the control signal without going through the plant. So in some cases, D is just zero. So we only have this part. And C here, it selects the output from several inputs. And B here, it yeah, it determines which state is affected directly by the input. Well, one way to do this, of course, you can just use this command in like the software in MATLAB. For example, so A, B, C, and D is again A is a matrix. So this is a 3 by 3 matrix, whereas B is a vector, right? Um, yeah, B is a column vector and C is a row vector, whereas D is, yeah, as I just mentioned, is just zero. So we could convert this into a transfer function by putting like this command ss. Ss means state space to tf. Tf is transfer function, and once we get this value of numerator and the denominator, we could construct the transfer function. Right? So this means that actually this is the order of the numerator. So it's like 0, or maybe we could start from the back, like 5 plus 25s plus, yeah, plus 0s square plus 0s to the 3. So this one is 0. And this is now 5 plus 25s plus 5s square, yeah, plus s cube. Right, so yeah, from this expression of numerator and the denominator, we can directly construct the transfer function, right? Which is yeah, 25s plus 5 over s cube plus 5s squared plus 25s plus 5. Okay, so that's what we can do with MATLAB, right? But I think it's also important that we also know the concept. So this is just an example for the third order system. Okay, so when there is no derivative term at the input of the system, so we are looking at this differential equation. It may be easier to set the states x1 and x2 and so on as the derivative of the output y. So suppose that we have this um, differential equation, right? So y with third derivative plus a1 y second derivative plus a2y plus a3 is u. So clearly u is the input and y is the output, right? So this differential equation is the same with the one we have studied in the beginning of this class, I believe, the beginning of this course. And this only considers output and input, right? So again, if you have other variables, you have to um, substitute them either to the output or to the input. And from this differential equation, we get the state equation x1 dot, x2 dot, x3 dot is this matrix. So this is clearly the matrix A. This is matrix A, and this is matrix B, and this is matrix C. And D, sorry, these are vectors. D is 0, right? So how do we go from here to here is, well, the step is we begin from y, right? So y is just, if we set y to be x1, then, the other is just 0, 0, right? So let's say y is x1, y is x1, which means we could convert this into like x1 triple dot plus a1 x1 double dot, right, plus a2 x1 plus a3 equals to u, right? And if we choose x2 as x1 dot and x3 as x1 double dot, then we have, so this would be x3 dot plus a1, so this would be x3, right, plus a2, this would be oh, sorry, this should be dot. Okay, so let me change this after this. And this would be y. Okay, okay. Yeah, so that would be a uh, x2, sorry, a2 x2 plus a3. Yeah, which is equals to 0. Okay, let me change this a little bit. Right, sorry about that. Yeah, so this should be x1 dot, and this should be just x1, and this should be x2, and this should be x1, right? So we don't get the constant here, right? Yeah, sorry for the typo. And then we get this equation, right? We put this into a matrix form. So what we know is this, that x1 dot is x2 and x1 double dot, which is x2, since x1 dot is x2, then x1 double dot is x2 dot, it's x3. So we arrange the matrix A, for example, it's x1 dot, x2 dot, and x3 dot. Yeah. So we have x1, x2, x3. Yeah. So this is 0, 1, 0. Why is that? Because x1 dot is x2, right? So it's from this one. I hope you can follow this. And x2 dot is x3, right? Therefore, it's 0, 0, 1. And lastly, we have everything here. X3 dot, oh, sorry, this is not 0, this is u. X3 dot would be minus A1, X3, and so on, right? So you have minus A1 here, you have minus A2, and you have minus, minus A3 first, because A3 is multiplied by X1, and this is minus A3. Sorry, A1 again. Yeah, flip this. Okay. Of course, because we have u here, it would be just 0, 0, 1. Right? So this is a single input and single output system because we have y is x1 and the u is directly changing x3 dot, right? Directly affecting x3 dot. And the C matrix is just 1, 0, 0 because we select y to be x1. So the message here is that actually there could be many other ideas or many other approaches for this. So this is just one of them. And well, later, or maybe not in this course, we will learn about this in control, right? So yeah, so consider this example now, where we have ys over us is this fraction, this transfer function, 1 over s plus 10 times s square plus 4s plus 16. So how do we write the state space representation of this? Right? So of course we should multiply these two fractions so that it becomes s cubed plus 14s square plus 65s plus 160, well, 10 times 16. And the differential equation here is that from this to this, I think it should be clear, right? So we have the transfer function. So this is y over u in s, both are in s. So u is y times s cubed plus 14s squared plus so, right? And s here means s cubed means third derivative, right? So it's just if we do a reverse Laplace transform, it would be u equals to y triple dot plus 14 y double dot and so on, right? Plus 56 y dot and plus 160 y. Yeah, sorry, I missed the y here. Let me change this again. Okay, so it should be correct one now. And this is again one of the state space representation. If we set y equals x1 and x2 equals x1 dot and x3 equals x2 dot, so A, B, and C could be written as this. So this is the same as in the previous explanation, right? So you put like the diagonal plus 1 row to the right as 1, but the last row is the coefficient of this um, of this denominator, right? So if you have for example 1 and plus 14s squared plus 56 plus 160, 160 becomes minus 160 because it is switched to the right, and 56 becomes minus 56 and so on. right? So yeah, there should be a simple way to obtain the matrix and vectors on the state space representation. And B is 0, 0, 1 is therefore, yeah, the input U is just affecting the state X3 directly, but of course it also affects other states, right? Okay, and C is 1, 0, 0 because we select Y to be X1, for example. Of course, there can be many other representations. For example, what if instead of instead of uh, instead of 1, we get like 5, for example, right? So I guess you can see what happens if this is 5. Well, it would be like so this is not 1 anymore, but it would be 5, for example. Right? So you change this one. Um, yeah, and there could be again, yeah, managed representation. I think the important point is that this uh, this representation should go to this transfer function. So if you want to check if the matrix is correct, whether it is correct or not, you can just convert this into a transfer function and see if that's the same, right, as the other representation models. Yeah, so yeah, this is just one of them. Just one of them. All right. So how about the other way around now? If we have a matrix like uh, this is yeah, actually quite similar. But now you have B, not just one, but you have 25 and you have minus 120, and C is 100. So how do we convert this into differential equation? First, maybe, or of course you can use the formula like G equals to yeah, I think like C Si minus A inverse and so on, right? Uh, but yeah, the system here or the matrix could be also converted into transfer function by converting this first into differential equation, right? Uh, so if we try to do this, suppose it's x1, x2, and x3 dot. So these are our first equation. It would just be yeah 0, 1, 0, 0, 0, 1, and so on. Plus, of course, this is the state x. I will just write x here. I think you can follow on your own. And this is 0, 25 minus 120. That should be you. Right. So by looking only at this matrix, right, you can write x1 dot is x2, whereas x2 dot is x3. So x3 dot is minus 5 x1 minus 25 x2 minus 5 x3 minus, oh sorry, so this yeah, it has another uh, um, yeah, another value here, which is 25. This is minus 1, right? Now we know that C is 100, which means that Y is x1. So if we begin from here, I hope we can recall this x3 dot is well yeah, x2 dot is x3 plus 25. All right, so x3 dot here, yeah, so or maybe let's write like, yeah, for example, we should do this in terms of x1. So x2 is x1 dot, for example, right? X2 dot, which means x1 double dot. Yeah, x1 double dot is x3 plus 25. So this should be multiplied by, so x3, uh, this is x1 double dot, x1 double dot minus 25. And then what is x3 dot, right? So x3 is x1 double dot minus 25. So we derive this again. That means we have x1 triple dot, right? Because the derivative of 25 is 0. Which means we have y triple dot from this equals to minus 5 y, right? Minus 25 y dot. This would be minus 5 y double dot. Also, you have this multiplied by minus 25, which means plus 125. And this would be minus, sorry, this is 125, minus 120, right? Yeah, so sorry, this should be u, and this x, yeah, so this should be u as well. All right, so x3 is x2 double dot minus 25 u. Yeah, sorry about u, I missed that. It shouldn't change the derivative because, well, it's, yeah, it's, you derive this with respect to x, so x1 double dot would be x1 triple dot, and there is no x term here, so it would just go to 0. Right, so y triple dot here is just, yeah, y triple dot plus 5 y double dot plus 25y dot plus 5y. Yeah, so that would be yeah, 5, right? So oh, I think I missed something here, that is 5. Okay. Okay, so I think I missed this part. So this should be minus 25 u dot, which means this should be plus 25 u dot, and this is 5, or yeah, 5, right? From this 5u plus oh, this is negative, plus 25 u dot, right? And by grouping y with u, I guess we can see the pattern, right? It's 1, 5, 25, 5, 1, 5, 25, 5, and this is 25 and 5, right? All right, so next example here is for the mass spring damper system. I think this is system that is very widely used. So suppose we have this system with this model. So we already have the model, and this is a second order system because we only have two rows, and we could write the state as y and sorry, as x1 and x2 from the output y and y dot. And what we do here is we divide this by m, right? So that it follows the structure that we already have before. But if you have other idea or other representation, I think it's also okay, right? So as long as it results to the same differential equation. So this would be y double dot b for m y dot plus k over m y, which is 2 over m, right? And yeah, we choose y to be x1, and this is y, yeah, y double dot y dot and y, which means that y dot is just x2. So x1 dot x2 dot. So what is this, right? X1. So this is x1 dot, which means, okay, I will just write the A matrix. It's not enough, so we don't have space. So this is 0 and 1 because x1 dot is x2, and x2 dot is actually, we convert this again to x2 dot, and this is x2, and this is x1, right? So x2 dot is minus k over m x1 minus b over m x2, right? And we choose y to be x1. So I think we should just simply understand. So from this equations, we could also show them as a matrix, or sorry, as a block diagram, which shows the internal process that happens in the plant, right? So you have, suppose that this is x1 is the position, and x2 is the speed. So here we can see how the position impacts the speed, for example. So if we try to control the position, we also need to know how the speed behaves, for example, although we don't necessarily need to control them per se, but it's important that important to know that the position here is affected by the speed or velocity, right? So this shows the internal process in the plant. I think that's was important. Of course, we could simplify this by writing this as a transfer function, but yeah, it's also useful to know yeah, how to represent the internal system on the plant itself. Okay, so yeah, I think that's the fundamental of the state space representation. I think if you are in control field, I think you will learn much more about this. Right, so next we will maybe just close over a little bit about the linearization and the nonlinear systems. Maybe not the nonlinear control though. So far what we have studied, such as like PID controller and transfer function and yeah, Ziegler-Nichols and so on, is for linear systems, right? And actually there are many systems that is or that are non-linear, And I think it's important to deal with that, right? So, for example, let's say in a UAV or in the like autonomous vehicle, you will have several states that are affected by like a trigonometric function and maybe like quadratic and so on. So uh, there are actually several ways to deal with that. Of course, maybe if you study more about control, I think, um, yeah, one approach is to use like nonlinear control method. Uh, well, we begin by analyzing the nonlinearity of the system, like a Lyapunov equation and so on. But the other approach is to linearize the system, right? To make the system linear. But it's not like a perfect approach because the system could only be linearized around certain point only, which means or which is called an operating point. So yeah, so linear approximation of a nonlinear system. So this is yeah, linearization that is valid in a small region around an operating point. Um, so if we have this nonlinear function, let's say that represents the nonlinear systems, we could approximate this by, well, maybe one approach that you are familiar with is by performing a derivative, right? By deriving this function at uh, some point or at one point, and then we say that around that point, this function is represented by this linear equation or by straight line, right? So this is valid only at this area. We cannot say that, oh, the system is always linear in this area, for example. So also, no, we cannot do that, right? So it is only valid in this, yeah, in this area, uh, this approximation area. So, um, yeah, commonly we use this. We use Taylor series to do this at point x 0, which is yeah, which makes the equation becomes fx uh, approximated by fx0 plus dfx over dx at x equals x0, and then multiplied by the difference. Well, for example, if you have this x square at 1, 1, comma 1, this will be linearized into fx equals 2x minus 1, right? So how we do this is, well, we derive this x squared to become 2x, right? And then um, at 1, 1 comma 1, this would be um, so the way we do this is like this fx. So fx, this is if we plug in the value of fx with x equals 1, it would be 1. Okay, so let me erase this. Right, so the derivative is 2x, right? So fx is approximated by 1 plus the derivative is 2x, 2x, but x is uh, 1, right? Which is 2, right? So this is 2, and then this is multiplied by 2x minus x0, which is 1. So 2x minus 1, right? Which is 1 plus 2x minus 2, which is 2x minus 1, right? So that's fx. And yeah, so we could approximate this at point 1, well, 1, comma 1, since this is the result is 1, uh, to this straight line 2x minus 1. Right? Well, another example is we linearize the same curve, the same quadratic curve here at x equals 10. So dy over dx is still the same, right? 2x, and if we plug in 2 times 10, it would be 20, 20, right? So this is x0 is 10, so this would be 100 plus 20x minus 200, which is 20x minus 100, right? So that's how it works. Yeah, I think that's yeah, quite simple. Just try to derive that and see, yeah, uh, how the system behaves at that point. Actually, there is like another terms, right? It's called a higher order terms, or HOT, uh, which we often omit, right? So the Taylor series is you have like one constant here, let's say, and then it's added with the derivative times the difference, and it's added by the higher order terms like the second derivative and so on. But often for like a relatively simple system, we stop here, right? So we omit the higher order term and we say that, okay, so this should be close enough, um, even if we omit the higher order terms. Right, so the other example is for um, two variables, yeah, a function of two variables. This is x and y. So x and y, z here is just fx, fxy, right? And fxy is yeah, is x squared plus 4 xy plus 6 y squared in this region. So typically we take the middle point here, so it's 9 and it's 3 here. Right. Oh, sorry, this should be 4. Let me change. Yeah, so this should be 4 plus 6. Yeah, and we use the same approach. Now we have two variables, x and y, and x bar and y bar is 9 and 3. So yeah, x minus this one would be 9 and this one would be 3. And we derive this, we plug in these numbers, 9 and 3 into these equations. So suppose that this is, let's say, K1. Yeah, so this is K1 and this is K2. K1 is just the derivative of f with respect to x, right? With respect to x, multiplied by x minus 9 plus, oh, sorry, this should be y, dy minus 3. Yeah, this should be a number, right? Since we plug in the value of x bar and y bar, right? Okay, let me revise this a little bit. Yeah, and the end result is we have z equals to 30x plus 72y minus 243, right? So this is clearly well, a linear system, straight line, straight line in the with three-dimensional uh, uh, field, right? You cannot write this in a simple way, or we cannot draw this function in like a two-dimensional way as we previously did. But since this is a three-dimensional function, well, it should be like a straight line across a certain value of x and y, right? At this point, 9 and 3. Right, and for the system, we have some characteristics called equilibrium point, which means that this is the point where the system does not move, or the state of the system does not move, which is x not equals 0, right? And if we linearize a differential equation, fx is 2x squared near equilibrium point, the solution, it would be x dot is just 0, because from the definition of the equilibrium point, we get x dot is 0, and yeah, we integrate, that it should be just a constant. Yeah, if the constant is 0, it would just be 0. And the derivative of this is 4x, which means at this at this point, this is 0, right? So we could differentiate this function to get 4x, and this is the near equilibrium point, because the equilibrium point is 0, right? Yeah, so I think this is just a closing over the equilibrium point definition. I think, yeah, we will, or maybe you will study this more in maybe other courses. All right. So let's move on to the next material. All right. So our last material for this course, we will discuss shortly about the body plot. So we go back to the linear system, frequency response of a linear system. And yeah, what is body plot, right? Or body diagram? Yeah, let me change this. Well, body plot is a semi-log plot of the magnitude and phase versus the frequency of the system. So yeah, frequency here, the context is of course the complex frequency, or could be, yeah, also could be approached by the imaginary frequency j omega. So body plot H decibel in decibel. This is 20 times times log with basis with base 10 of H. So H is the term of the factors of the transfer function. So how we do this is we factorize terms of transfer function, then each factor is plotted with magnitude and phase components. I think I covered this with this semi-log plot. So yeah, by the way, this is the semi-log plot. So it's a plot not in the linear axis, but it's in the logarithmic axis. So you see that the line here is getting denser and denser over time at this. So it represents the point at which we focus on the logarithmic scale of um, some certain points, let's say like 1 or 10 or 100 and so on. Well, and then after factorizing terms of the transfer function for body plot, we plot the magnitude and phase of each factor, and then the plot of each factor is summed into one plot. And we do this by using approximation, actually, approximation at asymptotic point, which means like this point Z1, for example, it's an approximation of the body plot at C1, but the exact value is not really crossing C1, but it's just above C1, right? So this will help if we sketch by hand instead of using program. If we use program, they will um, plot this exact value for us, right? But it's hard to draw this, precisely. So I think, yeah, approximation could be helpful uh, to obtain the general shape of the body plot, right? And yeah, it is developed by Hendrik Bode, I think. Um, yeah, yeah, maybe I think he is like yeah, prominent control engineers and control theorists. This body plot, I think it's very useful to know how the system behaves over different frequency range, right? So for example, if the h here, or the magnitude, it's called the magnitude plot, h is it's very small, for example. So this means that in that case, the system will get almost zero gain, or it will be attenuated quite heavily. But if h is large, then the system will be multiplied by some positive or positive gain, so that it becomes larger. So for body plot factorization, we could factorize this body plot into these terms. So h omega is the transfer function, which could be factorized into k, and then j omega, and then 1 plus j omega over z1. So this is the zero of the transfer function, right? So recall that there is like a pole, and there is like a zero of transfer function. And P1 here is the pole. Z1 is the zero, right? And the common terms, we have constant K, and we have pole or zero at the origin, J omega, and we have the first order simple pole zero, 1 plus J omega over Z1. And we have a second order pole zero, which is represented by this term, right? Yeah, so I think for a simple system, we need to understand how the factors, these factors work, right? So these are some common terms or factors for constant K. So M here is the magnitude, P is the phase. So this is phase, and this is magnitude. So magnitude is 20 times log base 10 of k, and the phase is 0 degree for positive k and minus 180 degree for negative k. So if you can guess, I think it's this plot. It's just a constant plot, right? A constant line, a straight line, constant value. Um, and the phase is for the angle here is 0 for positive k and minus 180 for a negative k. Then pole at the origin is 1 over g omega to the n. Uh, here the magnitude is minus 20 decibel per decade, or this would be the decibel value of this. And the magnitude is minus 20 decibel per decade. So note that this is the line that goes down, that decreases over time. So it's like this straight line, which gradient or slope minus 20 per decade. Decade means like from 1 to 10, it's like one decade. From 10 to 100 is another decade. Right? And for 0 at j omega to the n, or 0 at the origin, it's the magnitude is 20 decibel per decade. Now it's positive instead of negative, so this is for pole, which is minus 20, whereas this is plus 20 decibel per decade, and it's 0 at omega equals 1, right? So here the magnitude is 0, and the phase or the angle here is 90 times n degree. Okay, sorry for the delay. Yeah, so for the first order point 0, yeah, it's changed into for 0, it's changed into this term 1 plus j omega over z. So z here is minus 0, right? The 0 would be at minus z, and here it has a slope of 20n. The slope is 20n dB per decade with a corner frequency, or frequency at which the value changes, is at z, whereas for the pole it is changed into 1 over 1 plus j omega over p to the n, with slope minus 20 n decibel per decade. The quarter frequency is p, right? So p is the minus the pole, right? So the pole would be minus p, and the 0 would be minus c, right? And the phase would be either 0, 45, or 90 n for such values. Yeah, also for the pole, it would be 0, minus 45, and minus 90 n for another value, right? So this value would be determined again by this p. Now it's instead of p, it's just p over 10 and 10p, same as c. And for quadratic pole, the slope is steeper. Now it's 40 n and minus 40 n decibel per decade. And for the phase, it's either 0 or p or 0 or 180 n or 90 n, depending on the value of the frequency omega n, which could be determined by this by the transfer function or by this this arrangement of the variables, right, with omega and so on. And for the pole, it's the same, but now it goes down to minus 40 n decibel per decade. The damping ratio here is zeta, and the damping ratio here actually it determines how the plot goes in the around the corner frequency. So of course it's not like it's not like a discontinuous point here, but it should be like a smoother like this, for example, right? Okay, so this is one example of the body plot. We are asked to sketch the body plot of h, which is 5 times j omega plus 2 over j omega times j omega plus 10. So the first step is we factorize this factorize the transfer function, and I think one trick is we multiply this constant by the factor in the zero terms, and then it's divided by the factors in pole terms. So in this case, it would be 5 times 2 over 10 divided by 10, which is 0, sorry, which is 1. So we put 1 here, 1 times 1 over j omega times 1 over j omega plus 2 times 1 over 1 plus j omega plus 10. So this is the factors that are allowed for this because, yeah, we cannot use this as it is, right? We cannot use this as it is, but we have to convert this into these terms. And there are several terms here. So for example, this is 20 log base 0 of 1, which is 0, and it is just straight line, and of course it's just 0 really. 1 over j omega, which is the pole here, is with slope minus 20 decibel per decade without any corner frequency. So yeah, it goes straight down. So this is pole at the origin, right? So this is factor 2. Factor 3 is the pole, sorry, the 0 at 2. So it's a straight line, and then at 2, it goes up with the rate of 20 decibel per decade. 20 decibel per decade, and then yeah, it goes up, right? And then the last term or the last factor is at 10, which is the pole at 10 with the rate of minus 20 decibel per decade with frequency yeah, frequency corner or corner frequency at 10. So we have four lines here, right? The first is yeah, it's just 0, so it does not really have any line, but yeah, here it's the line that goes up, and these two are the lines that go down. And what we do is we just sum all of these lines. So here we have this part. It is from this factor number 2, and we have this part that goes up. This is for the factor number 3, and this is for the factor number 4, right? And if we add those 4 lines, or 3 lines rather, because the other one is 0, if we add those 3 lines, we will end up with this line in the red, right? So it's here, and then it goes up and goes down with the same slope, 20 and minus 20, so it becomes constant again, and it has another pole at 10, the first order pole with slope or gradient minus 20, so it goes down, right? So as the frequency goes up, the system produces a very small output, but if the frequency goes down, it produces high output, right? So that's how we can interpret the Bode plot. Okay, so these are maybe the general idea of the Bode plot. Okay, so the second example is we have this transfer function 200 j omega over j omega plus 2 times j omega plus 10. And what we do is we factorize 200 j omega over j omega plus 2 times j omega plus 10. And what we do is we multiply the constant by the factors in 0 terms, and we divide this by the factor in full terms. So 200 over 2 over 10. So it would be 100 over 10, which is 10. So again, we have several terms here. So this is the first one is the constant, 10. And the second is the 0. And third is the pole at 2, at minus 2. And the fourth is the pole at minus 10, right? So this is for 10, and this is for 0 at the origin, j omega, and this is for j omega plus 2, and this is for j omega plus 10. Okay. Now the resulting shape is like a trapezoidal shape here. So it goes up because of this, sorry, not this, because of this. And then it's constant here because it stops at 2, it's some value, but it has another term that balances this so that it becomes constant. But then when there is another pole, it becomes or it decreases until the gain or the h here in decibel becomes very small, right? So again, this is the summation of all of these 4 plots. Well, an easy way to do this, of course, you can use softwares such as MATLAB. For example, this is the example. If we put this function into MATLAB, you can use like the code numerator and denominator, and just type the command body, and you will have this body diagram, both the magnitude and the phase. So it's actually quite handy. This one is not an asymptotic one, but an exact body diagram. So yeah, it would be helpful to check your result based on this, right? Yeah, so num, and then here, of course, is numerator and the denominator, and this is, well, if you have 200 here and 0, it means that this is the 200 times s to the 1, and this is 0 times s to the 0. So this is just 200s, right? Yeah, and the denominator is the same, so you have s squared plus 12s plus 20. Yeah. And you can use also many other tools do this, including like some websites and some apps. So you can try to check this link. And yeah, for example, this link on top, they have this nice comparison between the exact value on the uh, black line, and in the asymptotic value is presented by this gray line, for example, and you can adjust, adding some factors or removing some factors and so on, and it would be useful, to learn about this body diagram, right? Okay, so I think that's all from body diagram. I think this is just just an introduction, and I think you will learn about this more in the future, especially in control. So yeah, thank you very much for your time. Um, I think the material stops here, right? So I think our exam would be until this body diagram, body plot, including so the linearization and the state space representation, um, and so on, right? Okay, so thank you for your attention, and I wish you the best in the future after taking this course. I hope we can gain something new, right? Although probably not much. Yeah, so all right, thank you very much, and I will close this Zoom and this video. Thank you.